photos are kind of the result of that explosion. So here you go again. So this is when it starts, and you can just see it sort of blasting out the side of the volcano. And then, this is what you can see afterwards. These, of course, are all tree trunks that have all been stripped, so you don't see any branches on it, of course. You're just seeing the tree trunk itself, and they've all been knocked over in the same direction by the blast. And this is to give you a sense of scale. So this is a person here. So these tree trunks, they have diameters that are sort of the same as the height of a person, so a diameter of 1 meter or 2 meters. These are huge trees that have just been knocked over on their side, snapped off their roots by the blast associated with Mount Helms. Again, giving you a sense of the power that's associated with them. Excuse me. When this ash then comes down the hill, down the volcano, if it starts to mix with water, or if there is a glacier, often these volcanoes are very high, and so they have sort of a glacier, by which I mean permanent ice, on the top of the volcano. So the volcano erupts, that ice is all melted, so now the ash and the hot air mix with this water. You then end up with basically a mud flow. So of course this is very dense. This flows down river canyons very rapidly, so it's a very destructive flow, and it can completely bury towns that are in its path. Obviously you can see these kids are standing on the roof of a building, and this you can see a whole area of homes that essentially have been buried. Of course, if you get caught in this mud flow, the instant the mud flow is like being in an avalanche. The instant the mud flow stops, it's like concrete. So you will not get out of that once it stops. So a very hazardous place to be. Okay, and then finally, there were lahars associated with part of the Mount St. Helens eruption, so you can see some of those lahars right here. Okay, so that's the end of the volcanoes. Any questions about this before we move on to the MyShake stuff? Yeah? Lahars? Lahars? Yeah. What is it? Oh, a lahar. What is lahar? Right. Sorry, lahar is this mud flow. A lahar is just the name for the mud flow, essentially. Yeah. Any other questions? Yeah. So granite is, first of all, granite means it's a silicic rock, and second of all, the fact that it's granite means it has big crystals. The fact that it has big crystals means that it cooled very slowly, so that means it can only have cooled deep in the Earth's crust. So wherever you see granite, that means you have deep continental crust that has then been exhumed up to the surface. So there isn't an association between the presence of a granite mountain with a volcano, because they must be on very different time scales. There was another question I think I saw. Yeah? Right. It's just the scale of the eruption. Yeah, so the area that's been covered isn't related to the silica content. It's really just how big is the eruption, and then sure, we think factors like wind, I'm sure, come into it as well. But really, it's the scale of the eruption. How much material is being pushed up into the atmosphere in a short period of time. That's what really controls it. Okay, last question, yeah. Pyroclastic flow is when you have, it's essentially just ash. So you start with, so it's magma beneath the ground surface. When it comes out, if it stays, it doesn't mix with anything, it doesn't explode, then we would call it lava, and that's what we saw in Hawaii. If it does explode, meaning that you fragment it and it's got air in it, and it goes up into the atmosphere, we think of that as being ash or tephra. A pyroclastic flow is when you take that ash or tephra and it kind of flows rapidly down the side of the volcano, and then a lahar is when you take that ash or tephra, you mix it with water, and it becomes a mud flow going down the side of the volcano. Suddenly I realize there's a lot of terms in here. Okay, I don't want to cut off your questions, but I want to make sure we have time to talk about the next thing that I want to talk about. So this is a unique opportunity, just to make sure everybody is on the same page here. This is not a normal part of this class, but this is a research project that I'm involved in, my research group is involved in, and it's a research project to really build the next generation of seismic networks. And the bottom line is that we need your help. Okay? I'm hoping that you will be excited to do this, to participate in this, because of, for the same reason you're excited about this class. This is about how we can detect earthquakes, get information about earthquakes. This is a brand new project, but our objective here is to build sort of the next generation global seismic network with literally millions of seismic sensors. Okay? And so here's your opportunity to be the first, 100 of those seismic sensors. Okay, so I'm going to introduce it very quickly, what we're trying to do, and then Chinkai here, who's a graduate student working on the project, he's going to come to you with the specific ask of what it is we would like you to do. Okay? All right, so this is a seismic hazard map of the world. You've not actually seen this map. You've seen seismic hazard maps for California and the western US, or actually perhaps for all of the US. This is a seismic hazard map for the whole world. And you know why the hazard is where it is for the most part. It's along the tectonic boundaries, South America, North America, throughout the sort of Europe, Eurasia swath around the Pacific Rim. So you know why the red zones are the high hazard zones. It's pretty much a simple question of plate tectonics at this point. And you also know that the way that we gather information about earthquakes, the way that we can mitigate earthquakes, come up with plans to reduce the effects of earthquakes is by having seismic data. And the challenge is that our ability to collect seismic data from around the world is very limited. Okay? We have good seismic networks in some places here in the US, Mexico, Chile, in Italy, in Turkey, in some parts of China, in Japan and Taiwan. These are places where we have good seismic networks, so seismologists like myself can get that data for the most part and understand the earthquake process. But there's some really big gaps in some parts of the world that have the highest seismic hazard. And this includes parts of South America, the Stans, Mongolia, Malaysia, Indonesia, the Philippines. So parts of the world that have very high seismic hazard, Iran is a particular note, I think, in this case, where we don't have seismic networks. And it's very difficult to know much about the seismic hazard because we just don't have any data. The other issue that we have with modern seismic networks is how dense they are. So California has one of the best seismic networks in the world, and this is the seismic network in California right now today, and the station spacing is about 20 kilometers. Japan has the best seismic network in the world. It has a regular station coverage over the entire country of 20 kilometers. It's really very impressive seismic network. But still, these are 20-kilometer station spacing. Okay? So this is, there's these huge gaps. As we know, the effects of earthquakes occur on very localized scales. One building or one block may be seriously affected by earthquakes while the next block is not. If you only have stations every 20 kilometers, there is no way that you can understand that process. Okay? So that's a real challenge when it comes to understanding the process that actually results in damage to buildings. So this is the seismic network, 400 seismic stations that we have in California that we actually use for our prototype earthquake early warning system in California that I'll talk about in the final third of the class. But what I wanted to do is show you that in context of this seismic network. This was a seismic network deployed by Nodal Seismic a few years ago in Long Beach. It's a 10-kilometer by 7-kilometer network with 5,000 geophones. Right? So it's 100 meter spacing. So it's a massively dense seismic network. Needless to say, this was not put out to understand earthquake hazards. Anybody want to guess why they would put it out? The Southern Californians amongst us? Yeah. Yeah. Oh. Okay, sorry. So anybody want to guess why they put out this network? Actually, to search for oil and gas. So they put out this dense network to try and image the subsurface to detect oil and gas. But they shared the data with us, and we can play with this data. And you can see some amazing things with this data. This is an animation that shows the seismic waves from a relatively small magnitude 3 earthquake radiating across this array. Okay, so the magnitude 3 earthquake, this is the Newport-Inglewood fault. The earthquake, of course, was up here. And what you see in this video is you see the seismic waves radiating across the array. And you can also see, of course, you would expect these waves to look like simple ripples on a pond, right? If you drop a stone in a pond, you have these nice circular ripples that radiate out. Well, you would expect the same in the Earth. But the fact that it doesn't look like that is because of the small-scale structure in the Earth, and it's that structure that means that this block is going to collapse, and the building next door is going to survive in an earthquake. So we need to understand the structure on this kind of scale. So the question is, how can we have a seismic network with this kind of density? All right? And the answer, we think, this is a research project, we think that the answer is to make use of the accelerometer in your smartphone. So every single smartphone in this room has an accelerometer in it. Okay? It's the same, well, it's not the same, but it's a similar kind of sensor to what we use in our traditional seismic networks to record earthquakes. So these smartphones, they have accelerometers. They, of course, we know their location from GPS. They have communication, so they can send their data out. It's the perfect seismometer. Okay? Well, there are some drawbacks. So if we could figure out how to harness these accelerometers in these phones, we could collect the data, and we would do that through the cloud. And we could use, first of all, we would just record data to use for research. But our actual objective here is to also use the data in real time to detect earthquakes underway and provide a warning of that earthquake. Right? So there's these two objectives, the research objective and the detecting earthquakes. Needless to say, there's some challenges, but there's 16 million smartphones in California. We currently use 400 seismometers in California. So all we have to do is persuade a relatively small fraction of smartphone owners to let us use their phones to record earthquakes, and we would have a massively enhanced seismic network. So that's the objective of the MyShake project, is to try and do that. So Chinkai is Chinkai is the lead on this project. He's done a bunch of research efforts to make sure that you can record earthquakes on phones, and we can distinguish an earthquake from the everyday motion. Right? When I get up, my phone, of course, is shaking now, but it's not an earthquake. And Chinkai has figured out how to separate the earthquake from the non-earthquake signal. And so we now have an app, and we have a back-end server, and so we are now looking for volunteers to put the app on their phone so that their phone, this all happens in the background, Chinkai's going to explain, so their phone will detect earthquakes, it will detect other kinds of shakes, and it will send that data to our back-end server so we can start to test the feasibility of building a seismic network using these phones. So I'm going to hand over to Chinkai. He's going to explain to you exactly what it is we would like you to do, but the bottom line is we are looking for you guys, those of you who have Android phones. Sorry, iPhone users, I'm an iPhone user. Okay, I'm also out because I'm an iPhone user. But the first version of this is actually an Android version. A later version may well include iPhones. So those of you who have Android phones, the bottom line here is we would like you to participate in this project, in the test, and Chinkai is going to kind of explain to you how we would do that.
Thank you. Okay, thank you, Richard. And hi, everyone. I'm Chinkai. I'm a graduate student actually involved into this project. Okay, it's starting now. Okay, let's just go back. Okay, so this project actually is a very fun project. So we are trying to turn your smartphone into a seismometer that in the future you might can record an earthquake just using these smartphones. So today I will mainly talk about the details of this app and how to get this app. So the app is called MyShake. So I record the screen from my phone. You can see this is the screen of my phone. And if I go to the apps, you can see the icon MyShake there. And if I press that one, so it actually starts MyShake app. So MyShake app actually now starting with these logos, which T-Mobile actually is collaborating with us. And then you can see this is the interface of MyShake. Basically gives you the earthquakes listed here in the last day above magnitude 2.5. That little dot actually is your location. And also you can see some of the earthquakes from the list here. If you press one of them, the map actually will move to the earthquake. And if you press that earthquake, you see that little circle there. So that's the earthquake, and it can bring you to the website of USGS. So this is the earthquake actually yesterday occurred in Alaska. So this is just some fun function of this app. But the main part of this app actually is to recording the data. So how is recording the data? Well, in terms of recording, so right now we have a simple steps actually to record the data from the accelerometers on your smartphone. So basically the first step is we require the phone keep stationary for 30 minutes. This simple step actually is to get rid of some human activities, like you walking with the phone, running with the phone. You actually generate a lot of movement. But if you keep the phone stationary for 30 minutes, most of the time actually this phone actually is sitting on the table or sitting in your pocket. And you can see there's a little a status bar there showing waiting for the phone to keep stationary. And then so the next step is after it's waiting there for 30 minutes. So the phone actually is ready to monitoring the background acceleration. So that means if I put the phone here after 30 minutes, if I move the phone a little bit or I touch the phone or pick up the phone, so this movement will trigger the phone. You can see the status bar there waiting for the trigger. If there's if you move the phone or if there's an earthquake, move the phone. So the phone will trigger and streaming data. At this stage, we actually save the data first on the local phone, and then when you have a power connection and also have the Wi-Fi connection, we will send the data back to our server. We will send 5 minutes data, 1 minute before the trigger, 4 minutes after the trigger. So altogether 5 minutes in case we miss the earthquake, the first part of the earthquake. And some more information about the app. So you can see this is a waveform actually recorded by smartphone. The right trace is recorded by my phone during the magnitude 6, so it's not earthquake. So how many of you felt that earthquake? Okay, I think a lot of people felt that. So actually my smartphone also felt that earthquake. You can see this is recorded on my smartphone, the right trace, and the blue trace is a seismic station, which is 8 kilometers from my apartment. I plot them overlap with each other, showing you the similarities between these two. So this is showing that during the earthquake, actually the phone can record the earthquake. So maybe next time your phone will record the next big earthquake. Okay, yeah, some more information or details about the app is, first, the app will run in your background, so you don't need to do anything about it. If you want to play with the interface, that's fine. But if you don't, just leave it in the background. It won't cost you anything. And then the second thing is, so we only keep the last 24 hours data on your phone. So the size is about less than 30 megabytes. So that means if you connected to your phone to the power and also connected to Wi-Fi, it will upload the data. But if you didn't connect it to your phone more than one day, that means we will override the oldest data. We just keep the latest 24 hours data. And the third point is like we're sending heartbeat from these phones every 2 hours to our server. The heartbeat means that we just make sure the phone, whether the phone is active or the phone is like inactive. Inactive means like you shut down the app or you don't have Wi-Fi connection. So this is the heartbeat message. You may use a very tiny amount of your data plan because it's sending like 1 data point every 2 hours to our server, but it's very tiny. And the next point is, so the battery usage, actually we are working really hard to reduce the battery usage so that it has the least like impact on your phone's battery. So it's quite similar to what your phone is in the idle mode. So basically this use a battery like less than 2% per hour we tested. And also the last point, so I think Richard talked about earthquake warning. Okay, so earthquake warning system actually is the big system or big project actually we are working on. So this project is using the seismometers to detect the earthquake once the earthquake occurs, so it can detect the earthquake within seconds and then send the data to the user, send the warning to the user. So actually we can use this earthquake warning message to trigger our phone to record if there's an earthquake. So this is the way actually we most likely to record an earthquake. Okay, the last part actually is how you get this MyShake app. So right now the MyShake app is a testing version. You can't download it like from Google Play directly. So the first step is like you need to send me an email to this myshake2014@gmail.com. And then the next step, I will add you to our testing group, the MyShake Google group. So all you have to do is to accept that invitation. Then you are becoming, you actually become like an official tester in our group. And then I will send you the download link. So basically follow this link, you can download MyShake app. But one thing you need to notice, like when you send me the email, you need the email account, actually exactly the same account on your phone. You need the email account on your phone to send me, not like a Berkeley account, which you use normally like to contact with your professor, but not on your phone. Yeah, hopefully, yeah, this is explained clearly. And also, thank you for your contribution to the science and to earthquake. Thank you.
Great, thanks, Chinkai. So again, I encourage you to all please sign up. If you have an Android phone or an Android device, send Chinkai an email. Sign up. If you decide you don't like it, you can always, of course, just remove the app. But the app's been built so that once you install it, you should never notice it. It has no impact on how you use your phone. Okay, so thanks for your help.